Hi, good evening, everyone. My name is Bhargava. Vincent, Dominique, and I are security researchers from the Technical University of Berlin, Germany, and we're here to talk about our automated fuzz testing framework called FuzzExMachina. This is going to be a longish talk, so I'll start with a brief summary of our work. FuzzExMachina, or FEXM for short, is an automated fuzzing framework. What this means is that it reduces to bare minimum the manual effort that typically goes into setting up a fuzz testing pipeline for software. Now, naturally, automating fuzz testing is a hard problem. So to tackle some of these challenges, FuzzExMachina has clever tricks up its sleeve, which we're going to talk about later in this presentation. We've developed FEXM with two use cases in mind, BYOB, or bring your own binary. In this mode, you can automatically fuzz software that you care about. And the other mode is large-scale distributed fuzzing. In this mode, you can use FEXM to automatically fuzz repositories of software packages, such as the Arch Linux package repository. We believe in eating our own dog food, so we've tried FEXM ourselves and found numerous bugs and crashes, which we'll disclose later in this presentation. Finally, FEXM itself is free and open source. You can check it out at the linked GitHub URL. Great, so here's a small outline of our talk. I'm going to provide some context behind our work and provide a brief introduction. Then I'm going to show you how you can use FEXM to automatically fuzz software that you care about, the so-called BYOB mode. Then I'm going to hand over the presentation to Vincent, who's going to get into FEXM internals and demo the bug dashboard, so to speak. And finally, Dominique is going to present our findings, a cool new feature called time warp, and finally conclude the presentation. And before that, he's going to show the demo. Great, with that out of the way, let me get started. I'm sure most of you are aware of what fuzz testing is, but for those who don't, it's essentially throwing corner case input at a program until it breaks. So it's a bit like shooting in the dark, but not exactly. And the idea is not new. In fact, anecdotally speaking, it dates back to a computer science assignment in 1988 provided by Professor Bart Miller at the University of Wisconsin, when he asked students to write the so-called fuzz generator program. The goal of this program was to provide an unpredictable input stream to test the resilience of Unix utility programs. Although this approach was rather dumb, it was surprisingly effective, and 1/3 of the Unix utility programs that were tested crashed. Ever since then, we've come a long way in making fuzz testing more effective. Security researchers quickly figured that simply random testing is not very effective because while it can quickly find shallow bugs, it cannot test deep portions of the program. So in the early noughties, some of the researchers proposed a so-called input specification guided fuzz testing. Here the main idea was tell the fuzzer what the program does by feeding it a specification of the program. One way to provide such a specification is, for example, tell the fuzzer what inputs to the program under test looks like. For example, let's say you're fuzzing the TCP protocol parser program. What you would do is define the so-called TCP data format so that the fuzzer can meaningfully fuzz test your program. Now, although this was much better than random fuzz testing, it had its own limitations. For one, you needed a specification to do such testing, and in several cases, getting a specification was difficult because either the program was poorly documented or for some other reason, specification did not simply exist. And the other problem was that when you drive fuzzer using a specification, you might not actually be testing undocumented features. So what happens is there is a divergence between specification and implementation, and you're targeting your fuzzing at specification, and that might not uncover bugs in undocumented features. So finally, in the late noughties, researchers proposed so-called feedback-guided fuzzing. And the main idea behind feedback-guided fuzzing is to do away entirely with having to require some sort of specification and let the fuzzer automatically learn about program behavior. One popular technique to learn about program behavior on the fly is coverage-guided fuzz testing. In this technique, what the fuzzer does is it essentially instruments the program such that it can monitor program coverage and then sees how different inputs that are fed to the program change program coverage, with the idea being that greater coverage indicates execution of some interesting portion of the program, and this is retained for future fuzzing. And feedback-driven fuzzing has been surprisingly very effective and found numerous bugs and vulnerabilities. This brings me to the state of the art. So today you find frameworks such as Google's OSS Fuzz and similar offerings by Microsoft and Yahoo, which take these advances over the years and scale it up at a massive level. So you have, for example, Google OSS Fuzz, which is known to churn out 4 trillion test cases per week. This is massive. So the idea is that these initiatives provide the infrastructure to fuzz programs and also the fuzzing toolchain. So all the developer needs to do is provide test cases, seeds, and so on and so forth. And the impact has been massive. For example, Google's FuzzBot has exposed over 1,000 open source bugs in various user space programs. And not only this, it has also uncovered in similar initiatives various bugs in the Linux kernel itself, which is used in millions of devices. Now, after Heartbleed was found in OpenSSL, some researchers at Google showed that had OpenSSL actually taken up continuous fuzzing of its code base, Heartbleed would have been found in a matter of seconds with the tooling that we have today. The GIF on the right shows you how quick it is to find a bug like Heartbleed using modern fuzzing toolchains. So clearly, we've come a long way and made a lot of progress. But yet, we still find buffer overflows in various programs like it's 1996. So clearly, there's a divergence between what exists and the kind of bugs we find today. So the question is, why aren't developers and QA teams not fuzzing yet, right? And the truth is actually that we are fuzzing, but we are fuzzing the sub 1%. What I mean is if you look at the scale of software that is shipped in a modern OS distribution, which is typically around 50,000 software projects, and the scale of, let's say, the most popular open source fuzzing initiative, which is Google OSS Fuzz, it only contains 150 software projects. So this is less than 1% of the software that is shipped to users, end users. And bear in mind that Google OSS Fuzz has been around for approximately 2 years now. So it's somewhat surprising that there are so few projects still, in spite of the fact that fuzzing toolchains have really made it easy for developers to test their code. So let me qualify the question that I posed a couple of slides back. The question is not that we're not fuzzing, but we're not fuzzing enough. We're not caring about the other 99% of software packages. So to understand why we might not be fuzzing enough, I did an experiment. So I'm going to present 2 perspectives about open source fuzzing initiatives such as Google OSS Fuzz. One, I'm going to present the perspective of a developer who is interested in enrolling their project into this program, and also the perspective of Google. So let's see what the developer perspective is. So here's what I did. I actually went ahead and tried to enroll a popular software package called OpenVSwitch. For those of you who are not aware of OpenVSwitch, it's essentially a software virtual networking switch, which does routine packet processing. So I went ahead and enrolled this project into OSS Fuzz. And in the process, what I found is that I needed to do 3 things. First, I needed to write a test program, which is essentially a C or C++ program, which accepts input from the fuzzing toolchain and feeds it to the API under test. Second, I needed to provide a seed corpus, or a list of files that are considered somewhat valid files by the program under test. For example, if the switch typically parses, let's say, TCP payloads, I need to provide a bunch of TCP payloads as the seed corpus. Finally, I needed to write a build script such that the software would be fetched from, let's say, GitHub, and then automatically compiled and linked to the fuzzer binary that would be run on the Google infrastructure. And to do this, I also had to provide a Docker file, which makes it possible to run the fuzzer in a containerized environment. So this is not, I wouldn't say this is too much work for the developer, but it's certainly not trivial, especially for those who have, let's say, little knowledge of fuzzing tool chains and the process of fuzzing itself. And then I present to you the Googler perspective. So what I did next was, like I said before, I was surprised that even after 2 years, Google OSS Fuzz has under 150 projects. So I spoke to a Googler called Kostya, who is closely involved with this initiative, and asked him, why is this disparity between the time OSS Fuzz has been around and so few projects, right? And this is what he said. He said that the biggest reasons people are not using initiatives such as OSS Fuzz is that there is huge inertia on the part of developers. There's lack of awareness, religious reasons, which I don't know what they are, but they exist, and no time, right? So then we got together and we thought, okay, we can't do much about religious reasons and lack of awareness. Of course, what we can do is come to platforms like Black Hat and ask you to fuzz if you're a software developer. So I'm going to do that and say, please use OSS Fuzz, please use FXM and fuzz your software. However, what we can do is try to address huge inertia and no time, right? So how can we make it easier for software developers to fuzz test the software that they care about, right? So what I deciphered from my conversation with Kostya and my own experience writing test cases is that the developer expectation is that I provide these so-called fuzzing frameworks my GitHub URL, and the fuzzing bot or the fuzzing service says, okay, I take your URL and I give you the bugs that I found, right? So that's the developer expectation. I provide you the URL, you give me bugs, and we are done. However, the reality is that it requires non-trivial amount of work on the part of developers. For example, providing a test program, seeds, and some configuration and a build script. And this can be quickly discouraging enough for the developers to not really take it further, right? So there's a divergence between expectation and reality, which I deciphered. So at this point, this was the main problem we were faced with, which is that if we take the route of Google OSS Fuzz, which requires developer participation, we pretty much encounter the same problems as they will, and we will not be able to scale up fuzzing further. So our main philosophy was to start automatic and go to manual only if necessary. So essentially the idea is we want the developer to do as little work as possible right in the beginning to enroll their project. But in case the automatic part does not work, we fall back to manual and provide the developer to investigate potentially manually. So with this design philosophy in mind, we've designed FXM. And at this point, I'm going to show you a demo of how you can use FXM to essentially fuzz software that you care about. In other words, the B-by-OB mode. And here, my colleague Vincent is going to help me with the demo. Thanks, Vincent. So what you're seeing is a terminal where we have set up the FXM toolchain beforehand. And now we are going to show you how you can run FXM on a binary you care about. So first, we're going to show you a configuration file that is required to run FXM. So let's do cat configuration file. So here's what we want the developers to provide us. The name of the software package, this is trivial, right? The outdir, which is where the results of fuzzing would be stored. The fuzz manager, or the mode in which you want to use FXM, in this case it's the B-by-OB mode, and the fuzz duration. In other words, how long you want the fuzzing to take place in minutes, so for 1 minute. And we optionally require a Docker file, which we'll show you. And the Docker file, in some respects, essentially provides a containerized environment for fuzzing. Here what we do is we use a pre-built Docker image, which we call Pacman Fuzzer. And essentially we clone the software that you want to fuzz, in this case JHead, which is a JPEG parsing library, and then essentially compile it and start our own fuzzing. So let's start fuzzing with these two inputs. And to do that, what you would do is essentially run FuzzExMachina and the configuration file. And at this point, what is going to happen is, let's hit enter. What's going to happen is FuzzExMachina starts automatically inferring the right invocation for the program. In other words, how do I invoke JHead so that parsing takes place? It's also going to infer automatically what kinds of inputs JHead parses, in this case, JPEG files. And when all of this is done, it's going to provide an optimal seed set to the program and automatically start fuzzing. Like you see on the dashboard, it's going to take a while to do all the fuzzing. So at this point, I'm going to hand over the presentation to Vincent, who's going to dig into FuzzExMachina internals and tell you in greater detail how we do the automation. So Vincent?
Oh, thanks, Bhagava. So yeah, with that out of the way, let me tell you what FuzzExMachina or FuzzExM actually is. It's a distributed large-scale fuzz testing framework, which basically minimizes the effort to set up a fuzzing pipeline to a point where it's almost completely automated. We leverage existing battle-proof software to build this automated framework, right? And using this framework, we started fuzzing hundreds of packages immediately. So here's how FuzzExM automates this pipeline. The only thing you need to provide is a package source, which can be either a BYOB configuration like Bhagava showed you, or it could be a package repository that you want to fuzz. So say you want to scale up, then you could tell FuzzExM to download packages from Pacman, say. Now, once FuzzExM has this package source or a list of packages that you want to fuzz, it crawls those packages for binaries, then infers some way to give those binaries user-defined input, selects a good set of seeds, then starts the actual fuzzing for you with a good configuration. And after that, it triages the crashes that came out of the fuzzing. And then in the last step, it hands control back over to you in a dashboard that displays the results in a very convenient way. All right, so let's look into each step in detail. And the first step would be the crawling binary step. So like I said, if you want to scale up, you do the following, basically. You choose a repository and then provide FuzzExM with a list of packages from that repository that you want to fuzz. Once you've done that, FuzzExM tries to download the source of the packages and compile it, and also add instrumentation where possible. It also tries to, after the compilation step, extract ready-to-run ELF binaries that we later on want to fuzz. So before we move on to the next step, let me quickly clarify what instrumentation means. Basically, Bhagava explained to you, we need to give the fuzzer feedback. And to give the fuzzer feedback, we need to keep track of the code coverage that we have achieved in a certain execution of the binary. We could do this either during compile time, and this results in a very fast execution speed, but it requires source code for the binary. And in the case of FuzzExM, where we want to do anything automated, we also need to be able to automatically build the binary successful, which from our experience, unfortunately, is not always possible. So following our best effort approach, we fall back to a slower runtime instrumentation, which also works for black box binaries. That means if you recall the package manager example, we try to build the binaries from source, but if that doesn't succeed, we then just download the pre-built binaries. All right, once we have our pre-built or our binaries, we need to identify a way to provide them with user-defined input. So to give you some intuition on what this means, say you would like to fuzz TCP dump. Then what you would need to identify is the parameter minus NVR and then the path to a file, so that TCP dump then reads this file. We would also like to identify that TCP dump actually passes PCAP files, but that's going to be a later step. So to formalize this intuition a little, once we have a binary in the repository, we need to identify two things. One, the parameter with which we need to call the binary so that it processes our user-defined input. And the second thing we need to identify is the input channel. So that would either be standard in, network, or a file given, or a file path given as a parameter. I want to quickly note here that normally network fuzzing is a non-trivial task. So what we do is we leverage great existing software. In particular, we leverage the DSOC library out of the Preini package, which hooks libraries. So it's a preloaded library which hooks network calls so that every time the binary reads from a socket, the input actually comes from stdin. So in that sense, input from stdin and from sockets are the same for FuzzExMachina. So to give you two more examples, well, we already had the TCP dump example, which would be NVR and then path to a file. And say you want to fuzz vget, then you would need to identify localhost 80 as the invocation that leads to user-defined input. All right. So to do this, FuzzExM employs a two-phase algorithm. In the first phase, we call that the collection phase. We collect potential parameter candidates where we assume those candidates could lead to the processing of user-defined input. We do this by parsing the help text of the binary. So in the case of TCP dump, for example, we would pass the help text, and that would point us to the -r parameter. And we also employ other heuristics, for example, brute forcing different parameter candidates that often lead to processing of user-defined input, like -f and then the path to a file. Then once we have all those parameter candidates, for each parameter candidate, we do a validation phase, which basically means we need to check if the parameter we tried actually led to the processing of user-defined input. Oh, sorry. So here's how we do this. Here's how we do this. For each parameter, we basically create a temporary dummy file and then try to give that dummy file to the binary as input with our parameter. In the case where we have a parameter that takes a path to a file, we just replace that path with the path to our dummy file. And in the case of a parameter that we suspect leads to the processing of input via standard in or network, we just pipe the contents of the dummy file to standard in. Remember, we desock the binary. And then after we've done this, we check the system calls of that particular execution and grab for open or read calls for our dummy file. And if the system calls for that particular execution contained those calls, then we know that our parameter indeed led to the processing of user-defined input. Okay, so once we've done that, we could already start to fuzz, but we would like to optimize our fuzzing setup a little more. So we want to select good seeds. Now, what are good seeds? A good seed is basically a valid program input. In the case of binaries that process files or process specific protocols, it would just be a sample file of the file type that the program parses. So coming back to the TCP dump example, it would just be a PCAP file. So to identify this, the algorithm we employ is based on coverage, and we do this under the assumption that the right file type yields higher coverage. All right, but before we can implement this, we need to acquire a set of sample seed files. We decided to crawl GitHub for that. And we did this because often developers include small test files in their repositories. So say you want to develop a JPEG parser, then you would include a JPEG file in your GitHub repository to do better unit tests. And this leads to the result that often in GitHub repositories, they are small sample files which cover a lot of corner cases, which is great for our fuzzing purpose. Okay, so what you can see here is a result of that heuristic. On your x-axis, you can see the different file types. And then on the y-axis, you can see the total coverage, the sample files yielded for the TCP dump execution I elaborated on earlier. And we can really see this peak here for the PCAP file type. So this would allow us to identify PCAP as the right file type and thus choose good seeds. While we were developing FXM, we identified 3 sort of stereotypical coverage patterns. One is where the binary processes a single file type. That's the one on the left, where you just have one peak. So it's pretty obvious that we have one right file type. Then there's another more or less obvious case where the binary processes multiple file types, and we just have multiple peaks. So that would be the case for an image parser, which can parse JPEG as well as PNG files. And we have a third case where the distribution, the coverage distribution is rather noisy. And in that case, we hand back over control to the user in a mode Dominic is going to elaborate on later. All right, now we have selected the seeds. We know how to give the binary input, so we can finally start to fuzz. In fuzzing, we try to assemble our own fuzzing experience into FXM. And the result is the following. We use American Fuzzilog, which is a well-known established fuzzer which has found a lot of crashes. We use fuzzing dictionaries where appropriate. So here we can leverage our file type inference algorithm. So say we know that the binary processes GIF files, then we can use GIF dictionaries for fuzzing. We use address sanitizers, which detect memory corruptions whenever possible. And we do network fuzzing via DSOC. We also schedule the fuzzing in a round-robin fashion so that each binary gets its fair share of fuzzing, so to speak. And we need to do that because we are in a large-scale setting. Once we fuzzed, we hopefully got some crashes, but those crashes are not really structured. So we need to bring some structure to the unstructured fuzzing output. And this is basically the triaging step. In the triaging step, we do 2 things. We classify the crashes according to their severity, and we try to deduplicate crashes so that we are only left with unique crashes. For this, we leverage existing tools, namely exploitable and AFL utils. And exploitable has a built-in heuristic to assess the severity and the uniqueness of a crash. We only fixed a functionality in exploitable, namely the handling of assign stack traces. So on this slide, you can see a sample assign stack trace. And what exploitable does, it takes into account 2 things to assess the severity of a crash and the uniqueness. So one is the type of the memory corruption. Say it's a heap buffer overflow. You would consider that more severe than a null pointer dereference, for example. And the other one is you try to calculate a unique hash of the stack trace to deduplicate the crashes. Okay, we finally arrived at the last step, the dashboard step, where we show you the results. And for this, I would like to ask Bhagava for existence, because I figured instead of showing you more slides, I will just show you another demo. Yeah. So what you can see here, Bhagava, could you bring the window a little bit to the right? Because I think it's cut off. Sorry for that.
How do I do that?
Okay. What you can see here is the FXM dashboard where you can see the results. And it shows you which packages you fuzzed and what's the worst crash that has been found in those packages. So say we found an exploitable crash in GNU PG, for example, and say we want to log into that. Then we can click on that package. Right. And then we can see all the binaries we have found in that package that we fuzzed already, and which crashes have been found for that specific binary. And in the dashboard, we can see, all right, we found an exploitable crash in KBX util, and we would like to look into that a little more. So we click on the binary. And here we see an overview of all the crashes we found, which are hopefully unique because we do the deblocking and their severity. Well, the last thing we could do if we want to explore the crashes a little more, say we want to debug or we want to earn some bug bounty, then we can view the crash log or the async stack trace, like so. Yeah, all right, so that's the dashboard. And as you might noticed, we have a lot of crashes that we found. So I will hand over to Dominic now, who's going to explain to you the results or findings and the time warp mode, which is the mode we hand back control to the user in case FuzzExM fails with the inference.
Thank you, Vincent. Yeah, so the dashboard, you've just seen it. And what better way to end Black Hat than with a few crashes, right? So let me present you the findings. What we did was we just ran FuzzExM against the Arch package repo for a few days. And we just ran it on the top 500 packages, which means we ran it on around 200 containing also binaries. Like the other ones are probably Python or something. We only ran it on one machine. Also, we could have done it on different machines because we're like using Celery, like large scale stuff. And well, this is how we started the day 0. On the first day, we had the first crashes, or on that day, but next day we were happy to find crashes. After the second day of those 200 packages, 29 of them had binaries that crashed. 12 of them were exploitable, according to our automated triaging. So that doesn't mean that others are not exploitable, and it doesn't mean that all of them are super severe bugs that can be exploited over the network. It just means that these are like heap out-of-bound reads or writes or something like that. And all of them were pretty popular. So we only took the 500 top Arch packages, including sysctl-, which I've never heard about, but it's part of LibreOffice, so there's maybe something there if you want to look into it. And then GIF2PNG, I just included it because I like GIFs. It's actually not one of the 500 most popular packages, although it should be. Yeah, so crashes, right? There's a heap buffer overflow in sysctl with a read, out-of-bounds read of 4K or something like that, which is obviously not too good. Continuing on. What if FuzzExM inference fails? What if we cannot do it fully automated? Well, we have so many packages. We ran it on 200 packages. Who cares, right? We cannot run it. We just drop it. No, that's obviously not true. That would be boring. As Bhargava said in the beginning, you've seen this slide before. When automatic mode fails, we fall back to manual. We introduced a new way to deal with AFL, which is easy to use, hopefully, and hopefully makes sense. So basically, as a user, you can use the AFL, or you can use the tool as you would usually, because you know things that other people don't, using time warp. Here, we have an unfuzzable source code, which is, please give me 8 characters, and then please give me the same 8 characters again. That's basically entering a password. Well, for a user, right, you read 8, please give me 8 chars, please give me the same 8 chars. It is extremely easy to do. However, for a fuzzer that can only see how if it reaches new basic blocks or not, and it can never see if it reaches the correct ones, this is, well, it takes, how long does it take to brute force 8 characters? It takes rather long, hopefully, else our passwords are really bad. Anyway, so using that, and below there would be the crash. So using that, if the user can use it until that point and then start fuzzing, we can find the bugs, despite this being an unfuzzable binary, just thanks to human user mode. Anyway, here's another bug. Write of size 8 in gdisk, which is part of GPT-fdisk. So, time warp mode. As I just said, it can start fuzzing at any point. So it will spin up the fork server. I'll go into that in a bit. At any given point in the program. It requires little technical knowledge, and it's fully integrated with FexSim. It's shown in the dashboard whenever FexSim feels that there's a need for it. So it's like, I'm not sure about if I inferred this correctly. Maybe you want to have a look at it yourself. And then you can choose if the binary is interesting or not. And like most of them probably are not. And then it'll generate test cases when you use the binary. So this is how AFL usually works. AFL spawns, or at least the fork server mode. AFL spawns its child, and the child then pauses at the very beginning, the instrumented child, and forks off for each new Fuzz instance. That way you use copy and write, and it's a lot quicker than if you would restart the whole program every time. And we added a command and control port, AF1, AFL, and a standard I/O port. So you can then give input over network, and then using the command and control port, you can go back to the beginning of the program, or you can start the fork server at any given point in time. JPEG Optim, another read of size 29. Let's do the time warp. So Vincent is going to assist me with the demo this time, and I'm going to cut short a little bit because of time. So this is actually the JHead demo that Bhargava started in the very beginning. This is our demo JHead. So this is why we only have one package here. It found a JHead exploit, or not exploit, but a bug after 1 minute. And then revive me is the package that we added. So on the very left, you see, on the very right, sorry, you see the time warp button. You can press it, yes. It'll take some time spinning up. Hopefully, yeah, it'll spin up a Docker in the background, so everything's containerized, and it'll connect to the binary. And here, this is the command prompt as you would see it if you would run the binary directly. So enter a char password here. That is the thing that you've seen before in the slides. Yeah, you can interact with it or something. I don't know. Yeah, okay, let's go back to the slides then. Thank you, Vincent. Okay, so this is the internals. This is how, I can't do a fuzzing talk without showing you AFL for once. So on the bottom, you see that it crashes after a very short time. After we've done, we enter test and test again using standard I/O, and then started fuzzing using the command and control server on the top here. Another crash. This time it's in JHead. JHead was the crashes you just saw. There were many more crashes actually. Out of bounds read. So to conclude this, how bad is it, right? If we have crashes in Bash, not in Bash, sorry, but in the package Bash, when you install Bash, you get main into HTML, you get like out of bounds read, out of bounds write, and the source, this is the crashing input, by the way. It's some random generator. So we crawled something from GitHub, and this is random stuff that it generated. It included CSS and whatever. It's kind of resembles probably a man page, I don't know. And meant to HTML even has this line in its intro. This program is rather buggy, but in spite of that, it often works. Okay, another bug, write-off says whatever. What happened to the bug? So in the beginning, we started off, well, okay, let's report some. We're gonna find some, so let's report them. Mostly either no response, or they didn't know how to deal with an ascend output and a binary blob. So the guys from libpng told us, please send a non-binary file as input. I don't know what a non-binary file would be, but if they would run the binary file in libpng, it would crash. Then there was another one, JPEG Optim, which was already fixed upstream, but just for a year, not downstream in Arch or upstream in Arch. It's just in the GitHub repo fixed. And then there's JHead that we just talked about. It's also in the Arch repo still, and it'll probably always stay there. Another read. And this was the answer of the author. Unfortunately, I don't have time to work on it these days. But at least he answered in 1 day. So I've heard about, IoT is so broken and nobody wants to fix bugs. But just look at your local repository. Here, that's the hyphen bug, write-off size 1 in some random library. So what do we want to do in future? It's not about the bugs. We're not here for the bugs. We're here for the tool. Obviously, a trained human can still do a lot better than a fully automated solution. We want to improve that. We want to let the machines take over eventually. Add more repos. So right now we have apt, which wasn't tested in the last week though. We have Pacman. We want to scale maybe GitHub. We started doing that a little bit. It's hard. You have to infer how to build a whole repo. That's not too easy. And we're still fuzzing pretty shallow. So, like symbolic execution at some point or something. We need to go deeper to stay in the meme category here. Lib sound touch, it's used in sound stretch. Oh, we downloaded something, sorry. Yeah, this is used in Audacity or something, I don't know. So to come back to the beginning, the TLDR. We have a fully automated fuzzing test framework, clever tricks up its sleeve. You can either bring your own binaries or you can fuzz distributions. And we found numerous bugs that you've just seen. And it's free and open source, starting now. It just got released to the public. Oh yeah, there's a bug in SQLite, not in SQLite, but inside its repo. So it wouldn't have been possible with lots of people's help and without their prior contributions that we used from open source community. More help is always appreciated. So go to github.com/fgzect/fexsem now and try it out. Maybe it works. Hopefully it works. Now it will work. If not, shoot us issues. If you have cool ideas, we're always happy to hear them. So to wrap it up, simple memory corruptions are still way too widespread. We don't know why we find so many bugs in simple tools. It should be easy to trivial to use AFL by this point. FexSem then tries to help out by automating this and it scales it to everywhere you want to go. There's no more excuses to not fuzz test starting today. So thank you. I think we have time left. If not, then we can continue in the rep room. That was FexSem. Thanks.